we've spent a lot of time talking about what a chemical reaction is. A chemical reaction is like when things, molecules, atoms, rearrange themselves to form something different. However, we've never actually talked about what really are they rearranging? What's changing? That's our focus for the majority of this unit. We're going to talk about what kind of different chemical reactions there are. And a chemical reaction really boils down to one thing: the bonds between the atoms. There's different ways that bonds can form, and there's different ways that bonds can break. But nonetheless, a chemical reaction is when new bonds are formed between two atoms. Now, those atoms could involve two different chemicals that first broke apart and then rearranged themselves in a different way and reformed new bonds. That's a chemical reaction, but again, all of it boils down to the bonding. Now, we're going to talk about two different types of bonding at this level. We're going to talk about ionic bonding and molecular bonding. So, today our focus is ionic bonding. We're going to talk about how metals and nonmetals can come together. All right, let's do this. So, ionic bonding, that comes from the word ion. So, when elements become electrically charged, they become what we call an ion. Ions attract each other because of their electrical charge. So, to understand how an ion comes to be, we're going to have to understand a little bit more about the atomic structure of each of these atoms. The periodic table, this beautiful, beautiful thing, tells us more than just patterns in the chemical properties. It also tells us how to build the atom, or at least using the Bohr model. So, we need to know two pieces of information to successfully build these atoms. We need to know what row they're in, and we need to know their atomic number. So let's get to it. Let's try building the hydrogen atom based on that information. The atomic number of 1 means that it's got exactly 1 proton in the core of the atom. So 1 proton in the core. That 1 proton is going to attract 1 electron. Now, if you recall the Bohr model of the electron, the Bohr model is kind of like the solar system model, but the electrons are in specific shells around the edge. So here's our hydrogen atom. It's got 1 proton, and then since it's in the first row of the periodic table, that means it's going to have 1 shell of electrons. That electron here will be in that first shell. So here's our hydrogen atom. We built it. It's got the atomic number of 1, which means it's got 1 proton and 1 electron, and it's in the first row of the periodic table, which means those electrons are going to be in the first shell. Now, we can keep going further than that. Let's look at another element. Let's go with sodium. Sodium is in the 3rd row, and it's got the atomic number of 11. So 11. So that means it's going to have 11 protons and 11 electrons, and it's going to have 3 shells of electrons. So how do we tell how many electrons go in each shell? Another thing about the periodic table, the number of atoms in each row tells you the number of electrons that can fit in that shell. So the first shell can hold 2 electrons. The second shell can hold 1, 2, 3, 4, 5, 6, 7, 8 electrons. The third shell can also hold 1, 2, 3, 4, 5, 6, 7, 8 electrons. This shell down here can hold 18. Same with this one. And then if we look at the wide version of the periodic table, these 2 bottom rows can each hold 32 electrons. So we're not worried about that far, but we can work with this. We know that sodium is going to have 3 shells of electrons. It's going to have 11 protons and 11 electrons. So let's build our sodium. So we'll label this sodium, Na. And we're going to drag in some friends. So remember that first shell can only hold 2 electrons. So first we should bring in all of sodium's buddies. It has 11 protons in the core. There's our 11 protons in the core of the sodium atom. Now we can also, those 11 protons are going to attract 11 electrons. So 2 of those electrons can go in the first shell, and then their negativity in that region is going to be repelling other electrons. So a third electron can't fit in there because it gets repelled out by the 2 electrons that are already in there. So it must go into a different shell. So that's where a second shell of electrons comes in. So our little lonely electron here, this one will go out there, and it can fit 8 electrons into this shell. So far we've got a total of 10 electrons for our sodium. We need one more. So it actually needs a third shell of electrons. So bring in our third shell here. And this shell can house that last electron. Now, atoms are most satisfied, they're most stable, is probably the best way to put it, when their outermost shell is full of electrons. You can already see a problem with sodium here. It's got 1 electron in this third shell. This third shell can hold up to 8 electrons. So there's 2 ways an atom can approach filling up its outer shell. The first way is it could take on 7 more electrons. If sodium could attract 7 more electrons, it would have a full outer shell. Another way is to get rid of this 1. If it could get rid of that 1 electron, it would be left with a full outer shell. That actually creates a more stable atom. So, which one do you think is easier for sodium? The kind of obvious answer is that it's easier to get rid of 1 electron than it is to gain 7. All right, so let's tuck sodium away over here. And let's look at another element. Chlorine, right there, number 17. So chlorine is in the 3rd row, and it has the atomic number of 17, which means that it has 17 protons and 17 electrons. Let's build it. So we've got 17 protons for our chlorine atom. It's going to have 17 electrons that are distributed amongst 3 valence shells. And the last 7, so we've got 2, 8, that's 10 so far. The last 7 are going to be in the last shell. So chlorine, it's got 17 protons, 17 electrons that are all distributed amongst 3 valence shells. So now how do these things end up bonding? We've got these 2 chemicals here. So sodium, remember, it's got this 1 extra electron, and chlorine is missing 1 electron. So these atoms normally, they're going to be, let's shrink them down a little bit. These atoms normally will be just doing the thing, vibrating in their space. Same with the chlorine, just vibrating around, and occasionally they might bump into each other. This is when a chemical bond can happen. So at this point, sodium and chlorine, their electron clouds are overlapping. And here is the key important step. When they bump into each other, this electron will actually satisfy both of these elements both of their desire to have a full outer shell. It can do that by donating itself to the chlorine. So now sodium has its outer shell is gone because it's full, because it's empty, sorry, I should say. Now sodium is it's nice and happy because it's got a full outer shell. It's got 1, 2, 3, 4, 5, 6, 7, 8. Or oops, how did that happen? You're not supposed to be there. It's supposed to be there. So there's its 8. So 8 electrons in its outermost shell. And chlorine also has a full outer shell. It's got what's going on there? 1, 2, 3, 4, 5, 6, 7, 8. What is happening with the chlorine? The electrons are going wild. They're not supposed to be doing that. Settle down, electrons. Stay where you're supposed to stay. Somehow we ended up with extra electrons somewhere. Oh, never mind. They're hidden amongst there. Sorry about that. All right, so chlorine satisfied, sodium satisfied. But here's the kicker. When sodium donated that electron to chlorine, because they bumped into each other, something special happened. Sodium still has its 11 protons in the center, so it's still 11 plus in the center. But if you count its electrons around the edge, there's only 10 electrons. So its overall charge is a 1 plus. This is an ionic charge. So it's become ionically charged because it donated an electron to chlorine. The same thing happens with chlorine, just the opposite effect. Chlorine, if you count them up, still has its 17 protons in the core, but now it's got 18 electrons whizzing around it, which gives it an overall charge of 1 minus. So they have both become ionically charged because sodium donated an electron to chlorine, who received that electron. That messed up the balance between positivity and negativity for the sodium and chlorine. And again, as I'm sure you can imagine, that doesn't satisfy them. They've got full outer shells and they're satisfied in that way, but now they've got an electrical charge. Atoms want to be stable. So what happens, just like with magnets, if you have a positively charged object and a negatively charged object, they are going to attract each other. So this chlorine atom will actually physically be attracted to the sodium molecule. The positivity and the negativity attract each other, and they will actually come towards each other, and their electron clouds will overlap because of the physical attraction between the positive sodium, the negative chlorine, and this is an ionic bond. We have created an ionic bond at this point. So let's bond another one. You guys don't actually need to do the atomic structures, that's for grade 10, but you can, what you guys do need to be able to do is recognize how the charges combine with each other. So calcium has the atomic number of 20 and fluorine has the atomic number of 9. So calcium is going to have 2 extra electrons in its outermost shell. Fluorine is going to be looking for 1 more electron. So how do they combine? So calcium, having 20 protons in its core, and around its edge it's got 20 electrons floating around. It has 2 extra electrons that it wants to get rid of in its outer shell. Fluorine, on the other hand, has I should say this is calcium. So fluorine, on the other hand, has 9 protons in its core, and it's got 9 electrons floating around its edge. So it's looking for 1 more electron. calcium wants to give up 2 electrons, and fluorine wants 1. So this 1 minus and this 2 plus. You need a second fluorine atom. So another fluorine atom can receive the other charge, and together they will satisfy each other. You'll end up with the plus 2 balancing with the minus 2. So this becomes CaF, but there's 2 F's. So this is calcium and fluorine together. Alright, gonna wrap up this video. There will be another one to go with it about how to actually name these things. So that new chemical that was created at the end there, it's not called calcium fluorine. It's got a certain set of naming rules to go with it. That'll be up next. Thanks for watching. Until next time.